to the viewer. This video will demonstrate the Blend-Invision project. Blend-Invision is a general purpose application for the unwanted object removal from the image. The object will be removed in such a way that it would look like that as if the object was not originally present in the image. Now, unwanted object removal is a common task in many computer vision and image processing systems. Here we have provided a method for removing object from image that is based on the in-paint interior method, which is a OpenCV inbuilt function. We have also followed various different paths before following this method and coming up with the final methodology, and we will discuss about them one by one. Let's first go through the basic modules of the project. So the first module is image segmentation. Here we will either divide the image into various segments, or basically we'll fetch the object that needs to be removed from the object. Now once we have retrieved the object or the position of the object that needs to be removed from the image, we'll mask these positions, and this will create another image which will act as a mask for the further processing. The last module, the third module, is blending or healing of the image. With the help of the mask image that we obtain in the second module, we will blend the object in the environment. So this can be done in various ways, and we have followed two ways. So one is the averaging method, and the second is the copying the neighbor values with some weights. So let's go through some path that we have followed. So the first one, the first experiment that we did was SLIC, which is simple iterative clustering segmentation. So in this process, first what we did is we created segments into the image to obtain the segment of the unwanted object. So here we can see that as we move down into the number, or we move denser into the number of segments, as the number of segments increase, it's hard to remove the object. There was also one other problem faced with this implementation, that as the number of segments increase, it was hard to label the images label the segments, as well as the labels can coincide onto a single segment. So this idea was dropped off. The second method that we used was the in-paint. We moved on to in-paint tailor method to determine what was the execution that in-paint tailor used, so that we can reconstruct it, or if there is any drawback into it, we can find out. So to first obtain the unwanted image, we used the HSV values. So here HSV values are manually incorporated to obtain yellow color, and therefore only this yellow apple has been obtained. But here you can see that the mask image has one single black dot. So what this one single black dot caused issue is that when we used in-paint inbuilt function, so that single one dot can create distortion in the blending part. So the takeaway from this particular path was that if we are using the inbuilt tailor method, then there should be only two parts into the mask image, and there should not be no overlapping between two. So because the in-paint tailor method had this overcome, we tried to implement our own in-paint method, and we looked into the in-paint tailor method implementation. So the first what it does is it takes neighboring pixel values, it assigns some weight to it, create a Laplacian matrix, and then fill in the masked region. But as the number of neighborhood pixels that you are taking, that is considered as radius. As you increase the radius, the complexity of the algorithm increases, and therefore it takes a lot of time. So even just one convolution in the scratch implementation of in-paint area was taking a lot of time. So again, this was also dropped, and therefore we dropped the neighborhood method and moved on to the average method, the neighborhood tailor method actually. So in the average function, what we did is, let's give you a little demonstration. So this is the code for the average. And okay, here I can use drag method to select this particular photo frame so that this should be blended with the background. And here you can see that it is blended, but here you can see, okay, there are some lines which can show, okay, there is some not so good blending here. And if we use the, so this was actually average blending, which used the average of the neighboring pixels, and not any weights or anything, just plain average. So the blending time of this particular implementation was nominal, and this approach was taken further for the comparison with the inbuilt function. Now in the average function, you can see that we obtain the unwanted image by creating a rectangular box. That rectangular box is created with the mouse callback function, which gives us the image pixel positions wherever the mouse action is taken. Either the left key is pressed, or we are dragging the mouse, or we are releasing the left key. So with the help of that, we obtained the mask region, and but the shape was strictly rectangular only. So one takeaway from this particular implementation was that we need to customize the mask region shape. Okay, so the next implementation was in that particular direction only, that we used the um, mouse callback function as a paintbrush, and wherever we drag the mouse, it will create a mask on top of that only. So no particular shape is required here. Let me give you a demonstration on that as well. So here I am dragging the cursor on top of the photo frame that we saw in the last demonstration, and I'm filling the area. Okay, I'm releasing it now. So the final outcome looks like this. Here we have used the inbuilt in-paint area method, which gives a very good result. The blending is quite exquisite. So what we have seen is that the average method and the in-paint area method, they both gives result in a nominal time, and we compared the uh, evaluation metrics in between those. We haven't used the mean square error because we have used PSNR. Now PSNR is peak signal to noise ratio, which internally uses the MSE. So just looking into PSNR works. And the second evaluation metrics that we have kept is blending time. So the actual blending of the image is what takes the most of the time here. Rest of the stuff is manually, or it depends on the human hands. So these two evaluation metrics have been captured here. Four image samples that we have shown here, and the techniques we have used are average blending or in-paint inbuilt method. So the PSNR value, higher the PSNR value, higher means peak signal to noise ratio, higher this value is, this value is calculated in decibels, the better is the quality of the reconstructed image. So we can see here that the average blending method gives a PSNR value low in all the four samples as compared to the in-paint area method. Also, the blending time, or the time taken for blending the unwanted object with the environment, is very low in the in-paint area method as compared to the average method. The blending time is captured here with the help of tick counts. So that gives a frequency, and um therefore we can capture this blending time in sequence. Here are the same 4 images results. As you can see, the average is taking a rectangular box, and therefore the blending part can be easily distinguished from the rest of the image. So the conclusion here is that we can implement the IITJ method from scratch, but it will require a lot optimization to take down the algorithm execution time, and the average function works nominal, and the IITJ methods works best here. We have also reconstructed more than 100 images, out of which most of the images are taken from the internet, and a few are captured by the camera in the campus itself. The limitation here is that we are doing just uh, in the average blending method, we need to define the start point and end point, which will and then only we can obtain the average of the neighboring pixels. And in the in paint method, we had to make the mask with the hands itself, and we had to make sure that there was no single dot in between the mask or the unwanted object region, so that there won't be any distortion in the blending part. Future scope of the object would be that we would like to make the selection of the object dynamic, and we would like to increase the number of the iterations also, that not just one iteration give out the final result, but we can modify the intermediate result.